To all of you joining me for this video, thank you. I hope you're all having a good day. We're looking here in a very comprehensive manner this specific integral form, but in the form of developing a formalized template, an antiderivative template for this type of form. You know, you've seen this in trigonometric substitution or in trigonometric integration. You can very well handle this with a good way, which is the trigonometric way. You know, when you're looking at something like this, you're thinking about secant square x minus 1 is equal to tan square x. This right here very well mimics what you see over there, and you bring in the tan square. And we will show you a better way in addition to that. Let's look at this. If a prime represents what you have over there, the a, we can develop a series of substitutions. Then x is equal to a theta d theta. You can bring all of that into the picture over there, and when you do so, you have here a secant theta tan theta d theta, and you have down over here, you'll have a square secant square theta minus a square. Remember the forms x square minus a square minus x square, and x square plus a square. These are the three forms we talked about in trigonometric integration. Anyhow, when you isolate the a square, you have a secant square theta minus 1. From all of this right here, you can very well bring in that identity and substitute it for a square tan square theta, and you know this right here is nothing new. You can bring in that. When you do all of that, you can very well cancel out things. When you cancel them out, the a cancels out, the tan cancels out. You'll have in the numerator secant theta d theta, and in the denominator you'll have a tan theta, but the a can come out as 1 over a, and you'll have tan theta. And you know, you're looking at this secant theta over tan theta, and you can simplify this. Secant theta is really 1 over cosine, and tan is a sine over cosine, and you'll have 1 over cosine times cosine over sine. You'll have 1 over sine, which is cosecant. All of this will simplify to give you a cosecant theta in that integrand. You'll have a 1 over a, and then you'll have a cosecant theta d theta. Then antiderivative for this is not hard. It's a minus natural log cosecant theta plus cotan theta plus c. But let's not go to the plus c because we still have to do something with that. These thetas can very well be developed from here. You know, theta based on what you're seeing is equal to arc secant x over a, and you have to utilize that to develop a triangle. So let's do it. You have here theta, a right triangle, secant is x over a, so this here must be x square minus a square. Now utilizing these relationships, you bring everything into this form. You'll have minus 1 over a, and then you'll have natural log. Cosecant of this theta based on this will be x over root of x square minus a square, plus cotan, utilizing this triangle, the cotan theta will be a over root x square minus a square. Consolidate everything over here. So let's consolidate everything here within the absolute value. You have minus 1 over a natural log. Remember, this is the entire procedure we're utilizing to develop that formalized template. Then we'll show you a better way of doing it. You have this x square minus a square, but this root x square minus a square, using the properties of radicals, can be broken down into x minus a in a radical and x plus a in a radical. See, this is equal to exactly what you see right over here. You can simplify this right here is to the power of 1, this here is to the power of 1 over 2. You can cancel this out and make that under a root. So you'll get minus 1 over a natural log. You'll have root x plus a over root x minus a. You can use the properties of radicals here again. You have natural log, you have x plus a over x minus a, all of this to the power of 1 over 2. See, I've put everything here under a unifying radical, which I brought out. This can come right here and attach with this 1 over a, and you'll have minus 1 over 2a natural log. You'll have x plus a over x minus a plus c. This right here is our formalized template for anything which has this appearance. In terms of the integrand, an integral of that appearance will generate you an established and a widely accepted formalized template to be that 1 over 2a with a minus natural log x plus a over x minus a plus c. That right there is a very good template. However, this template can be again modified in a better way. To change it, you see you have a minus here. You can bring the minus here as an exponent. Let's look over here. You have this minus, you can bring this minus as a exponent of this natural log item over here, and that flips everything around. So everything here in essence becomes 1 over 2a natural log x minus a over x plus a plus c. This right here is a better template because you've gotten rid of the minus. The minus allows you to flip the numerator and the denominator around. It's just like you having an expression to the power of -1. It makes a reciprocal of it. That's exactly what you get. You have a flip effect over here. So that right there is equivalent to that. And this is the item right here you should always be thinking about versus this. Get rid of the minus and flip these around and you're good. So now I've shown you one way of doing it. Let's show you a better way of doing it. The better way will yield you exactly the same thing. You're looking here at everything which looks like dx over x squared minus a squared, but you're looking at it in the forms of factors, and you know where we're headed. We're headed towards partial fraction decomposition, which is a better way because this right here can be factored, and you could utilize it for the same type of antiderivative which look like that. Dx over a squared minus x squared. You wouldn't utilize it for an antiderivative which was a squared plus x squared because you can't factor this any further, but you can certainly utilize it for these cases, and you know these three cases over here are all present in the trigonometric integration chapters or in the trigonometric integration topics. We have all of these three forms. Anyhow, you look over here, you have two factors over here. You'll have a over x minus a, and then you'll have b over x plus a, which will equal to the numerator here 1 plus 0x, a placeholder. You'll do a times x plus a plus b times x minus a is equal to 0x plus 1. Open this up, you'll have ax plus a, and then this a plus bx minus b, and then that a, that's these a's carrying through 0x plus 1. Isolate the common terms. Utilizing these linear factors, we have a plus b is equal to 0. That's from these linear terms. But then we also have this. You can't get rid of the a's over here because those a's would have a certain meaning. The other expression is a with the lower a minus b with the lower a is equal to 1. If you're looking here, a is equal to minus b. You can bring a minus b here. You're looking at minus ba is equal to 1. You can essentially ignore this a for right now and just bring it outside, and you're looking at something like this. You see how you're looking at that? A has been pushed outside. In that instance, you're having now minus 2b is equal to 1, and then b here is equal to minus 1 over 2. And then you can very well bring this a exactly down with it, and b is equal to minus 1 over 2a. If b is equal to minus 1 over 2a and a is equal to minus of that, then a over here should certainly equal to 1 over 2a. And that right there is your one factor, that right there is your one factor. Just don't eliminate this factor because it very well plays along because it has a good meaning to it. You're looking at everything here with regards to your template now, and bring in those a and b values into this template and you'll see how everything will take form. A is 1 over 2a, so you are looking at 1 over 2a x minus a plus b is a minus 1 over 2a. So let's bring in the minus. We'll do minus 1 over 2a into x plus a. Now you're doing the integral of all of this. You can bring the 1 over 2a out in both instances, 1 over 2a, and then you're looking at all of that. But rather than looking at all of that, let's do the antiderivative. The antiderivative of 1 over x minus a is natural log x minus a. Then you have this minus. The antiderivative of this, remember I've pushed the 1 over 2a out like it was part and isolated out. The antiderivative of this is natural log x plus a. Now when you combine this, you're looking at 1 over 2a. The difference of logs is equal to their quotient, right? Natural log x minus a over x plus a, and then you have plus c. And your template has been derived in a very more easy procedure. In the previous procedure, when we ended up at our antiderivative, then we had to bring in the inverse trigonometric functions. We had to create the triangle, then we had to go use the properties of radicals and do all of that algebraic simplification to arrive at this. But here we have arrived at it much quicker. For those cases which very well mimic these forms and a squared minus x squared, the partial fraction decomposition route is much more easy because it directly gets you to where you need to be in terms of your template much quicker and in terms of your antiderivative much quicker. So how do you actually put this into effect? And remember, my main message here is this: the PFD technique, partial fraction decomposition, is relatively more superior than using the trigonometric integration procedure which I showed you prior to this. But how do we actually use this? And let me show you this template very quickly by means of 3 examples, but those examples are literally seconds each. That's all they are. We are just using the template now. You know we've derived this template and this template using this integral form. So let's put it into effect. So at any time you have something which looks like dx over x squared minus 4, here you know a is equal to 2. come right over here, you'll have 1 over 2 times 2, which is a 4. You'll have a natural log x minus 2 over x plus 2 plus c, and then you'll be done. Your answer would be right. If you had something which looked like dx over x squared minus 5, here you know a is equal to root of 5, because a value is always your root of this perfect a. This right here represents a squared, so you have to determine the root. Here this is a squared, a is root of 5. Put everything here into the template, 1 over 2 root 5, and then natural log x minus root 5 over x plus root 5 plus c. Lastly, we can look at this. If dx over x squared minus 9 represents our integrand, here we know a is equal to 3. Bring it right here in places of a, just your 3. You'll have 1 over 2 times 3, which is a 6. You'll have a natural log. You'll have x minus 3 over x plus 3 plus c, and you are done. That's the benefit of you knowing this template. This template is for this form right here, and you can do a similar template procedure for a form like this, a squared minus x squared, utilizing the partial fraction decomposition technique, because this is indeed factorable. Okay, and with that, I thank you for watching this video. Have a good day.